Alright, so let's talk about the method of Lagrange multipliers. So the idea is this: we're given some objective function of n variables, and we're trying to find where this function is largest or smallest subject to some constraints. So we'll state the constraints as a system of equations, essentially. So let's see here, do some counting. If we have g going from Rn to Rp like so, then basically this thing is something like a what? It's actually something like an n minus p dimensional. Usually you might call it a constraint surface, but that's of course an abusive language. Constraint. Let's say constraint manifold. All right. So suppose that there is. Let's suppose that f of, let's say, letter I haven't used, q is equal to extreme extremal value. All right. Then we can draw a picture of this, right? Let's say that, let's just, sort of a heuristic picture, but a picture nonetheless. Suppose that this, and I also suppose it's an extremal value on the constraint manifold, right? So suppose that this is the constraint manifold M, right? So extreme value on, g of x equals to c. I haven't even given it a name. Well, I guess I called it M. So let's call this thing M. Solution set to that, let's call it M, all right? So Q is some point on here, all right? So think about this. If it is going to be an extreme value of the objective function on this surface, then if you were to take a curve on the surface, right, which could be a manifold, of course, right? If you take some path which goes through Q, right, and let's see here. Suppose we would take this would be gamma of t, right? And without loss of generality, we can suppose that gamma of 0 is q, okay? Then to say that gamma of t is on M, what's that mean? That means that g of gamma, right, of t is equal to c. Okay, great. So what's the relation between this, this path on the constraint surface and, well, the g? I mean, we can differentiate this, right? Differentiate this, what we get? We get g prime of gamma of t times gamma prime of t is equal to 0, right? In fact, that's true along the whole curve. Let's see here, but what does this mean? In particular, it's so, t equal to 0, special case, but, certainly if we plug in t equals to 0, we get that g prime of q, right, times gamma prime of 0 is equal to 0. In other words, let's put it into more. So in other words, gamma prime of 0 is oh, curses. What's this mean? That means it's perpendicular, right? To what? To the gradient of the first vector, the first component function of g at q, the second component function's gradient at q. I mean, maybe we should put transposes on these. You'll forgive me for not putting transposes. The gradient of how many constraint functions? There are p of them, right? So all of these, so here I'm introducing that we can write g in terms of its component functions. There's g1, g2, how many other? Well, there's p of them, right? So to have this equation is to say that the gradient of the first one dotted with that is 0, the gradient of the second one's dotted with that 0. I mean, this just goes back to the definition of Jacobian matrix, all right? So we got all this. In other words, what's this mean? This means that, so gamma prime of 0 is perpendicular to all those, right? And what else? Well, on the other hand, we haven't even used that q is an extremal point, right? If we define the function h, right, and say h of t is equal to f of gamma of t. We can do that. Then certainly h of 0, right? Think about this. What would h of 0 would be f of gamma of 0, which would be f of q. That's an extreme value, right? We're assuming that exists. So this h, which is a function from the reals to the reals, should have a extreme value at t equal to 0. So of course that tells us that h prime of 0, which by the way would be what? That would be gradient of f at gamma of 0 times gamma prime of 0 is equal to 0. Aha, so we just learned this says that and gamma prime of 0 is what? It is perpendicular to what? The gradient of f at, what was gamma 0 at q? All right. So what must this mean? If the velocity is perpendicular to all these, and the velocity is perpendicular to all of those, what does that say about the, what is the relation between these and those? They're both in what? Try to draw my thoughts together here. So notice that the gradient of g1 at q, gradient of g2 at q, and on down the line the gradient of the pth component function at q, and the gradient of our objective function at q, right? All these guys. These are all perpendicular, right, to this tangent vector, gamma prime of 0, right? These are all elements of the perp to the tangent space at q to m, right? Because notice that, what curve did I take here? I took actually an arbitrary curve, right? And it doesn't matter how you approach q. If this f of q is an extremal value, it shouldn't matter. It should still be that this is 0, and of course this is just chain rule, and you know. But on the other hand, we also had that theorem which said that the this thing, right? What's the basis of the perp to the tangent space? Well, it's these guys, right? By definition. So using the fact that these form a basis, we can write the gradient of f as a linear combination of those. So in other words, the gradient of f at q should be equal to something like lambda 1, the gradient of g1. Man, I regret writing this q of q, plus lambda 2, the gradient of g2 at q, plus plus lambda, how many do I got? I got p of them. Lambda p, the gradient of g, gp at q. So this equation right here, if there is a answer, if there is an extreme value for the function, then we should find this relation between the gradient of the objective function and the gradients of the constraints. And that is the method of Lagrange multipliers, that you look for solutions to extreme value problems by trying to solve this problem. Now, of course, there is much danger here because it assumes that there exists a solution. Now, typically you just have, you know, in calculus 3, most people only look at the gradient of f is equal to like lambda times the gradient of g, right? So this would be the situation where we have just one constraint, you know, but if you have many, this is how you do many. Some calculus books have this, some don't. I'll show you some examples of that because I think that's the new thing. But before I do that, let me just warn you some of the dangers of Lagrange multipliers. So, you know, you can try to find Lagrange multiplier solutions sometimes. They may or may not exist. There's a theorem. The basic theorem that keeps you out of trouble is that if m is compact, all right, and f is a mapping from, say, m to the reals, then f attains a minimum and maximum values, min and max value on m. So this compact, what's compact mean? Well, maybe best thing I can do is give you an example. So All right, sphere, Sn, or n sphere is compact. On the other hand, planes, lines, hyperboloids, if I can be so foolish as to try to draw them. Not compact, not compact, not compact. The reason this is compact is because you can put it in a box, basically. Well, you can put it in a larger ball, right? There exists some kind of bounding ball. For us, that's what compact means. It means that there's a way to encapsulate inside some finite ball. You can't do that with here, right? No matter how big you make the ball, the plane goes on and on, the line goes on and on, the hyperbolic paraboloid goes on and on, whatever. But compact things, there's an extreme value theorem, all right, which I'm not going to prove in here. That's basically a topological result. Extreme value theorem states that there exists the min and max values. So if you try to apply the method of Lagrange multipliers to something that doesn't actually, have, let's see here, let's try it out. Suppose we look at like f of x comma y comma z equal to x, and I don't know, let's look at the constraint. I'm trying to think here. How about g of x, y, z equal to, here I'll make it a little bit complicated. Let's say y and z, right? Y and z are both 0. Okay. So let's see here, method of Lagrange multiple. So we have two constraints in this case. So we would try to solve the gradient of f is equal to lambda 1, the gradient of y, plus lambda 2, the gradient of z, if we follow the method. So that would give me what? This might, I don't know what's going to happen there. Just made it up. We'll see what happens. The gradient of f is 1, 0, 0. That's supposed to equal to lambda 1. What's the gradient of y? Well, 0, 1, 0. What's the gradient of z? 0, 0, 1, right? So we got to solve the equations. What we got here? Oh, this one actually failed. This is my luck. Yeah, fine. Okay, fine. I guess the method didn't fail here. I mean, these equations are, oops, right? Curses. Well, anyway, you can come up with examples where, because your constraint surface is not compact, you get sort of false positives for the method. I'm trying to think of a good example, something like that. Let's see here. You could have something like your constraint curves look like this. Here's some level curves to the constraint. And then, I mean, and then maybe the x, what are the level curves to x, right? So if you do that, you're going to pick up on these 2 points because these are the places where the gradient to the constraints match the gradients to the objective, like they're collinear. But, this could be something like -3, -2, and then over here is like 2 and 3, something like that. And so if you did that, and you find that these are collinear. Oh, I'm sorry. I should just pick, I'm an idiot. You guys already knew that. Let's see here. So scratch the 3's. All right, so the constraint surface is, the constraint curve in this case is this hyperbola, which opens up like that, right? So this hyperbola, if you look at if your objective function's x, then the gradients are going to line up here and here. So it's going to make it look like the minimum's -2 and the maximum's 2, right? That's what the method of Lagrange multipliers would say. But it's nonsense. Of course, this green curve goes on and on that way and goes on and on that way. There is no minimum. There is no maximum for the x function subject to the green curve. So Lagrange multipliers are dangerous in the sense that they can give you false positives or sort of false negatives. But if you're dealing with a compact constraint, then you can be assured that it works. Now we do use Lagrange multipliers on things which are not compact, and we just have to be careful. Okay, like example 9 is such a thing. This is actually example 9 from Edwards Advanced Calculus. I just thought it'd be good to show you guys this. So here's the deal. We're supposed to find the minimum distance from x squared plus y squared equals to 1 and x plus y equals to 4. So this is a problem you probably were not assigned in Calculus 3, because we've got, the Calculus 3, they typically give you a point and then say find the closest thing to closest point on the curve to that given point. So this is, a different kind of problem, because if you've got two curves, it's really a four-dimensional problem, because you can move this or that, Oops, sorry. You can move this or that. Okay, sorry. Anyway, so we're trying to make this as small as possible. That's the squared distance, which of course will minimize the distance. And so we've got two constraints. We've got g1 has to be 1. We got g2 has to be 4. Lagrange multipliers looks like this here. That's just saying that the gradient to the objective function is in the normal space to the constraint. All right. The constraint manifold here is a two-dimensional subset of a four-dimensional xy uv space, right? Now this is what the gradient means. It's x and y and u and v derivatives. So you take that and you act on these g's and you get this. Well, you get that from the f. It's easier for the g's. Like this just gives us 2x, 2y, and there's no u's and v's, so 0, 0. When I differentiate that, I get 0 for x derivative, 0 for y derivative, 1 for the u derivative, 1 for the v derivative. So, great. Then you have to solve all these at once. So we have to solve these equations, the Lagrange multiplier equations, and he points out, like, I'm just following Edwards basically. He's like, okay, look at these, lambda 2 equals lambda 2, which tells us that x minus u is y minus v. He gives a little argument for why lambda can't be 0. If you assume lambda is 0, it gives you a contradiction to these constraints. So lambda is non-zero. If lambda is non-zero, you can divide by it. And that gives us that you can solve this for x, you can solve that for y, and but remember x minus u is y minus v, so these are equal, which shows you x equals to y. Well, once x equals to y, that's pretty nice, because then we go back up to here. Knowing x is equal to y, that gives us that u is equal to v, so knowing x is equal to y and u is equal to v, it's easy to find the points are plus or minus 1 over root 2, and u and v are both 2. In other words, we get that the points 1 over root 2, 1 over root 2, and minus 1 over root 2 for the circle are extremal in terms of their distance from 2, 2 for the line. Now that is a beautiful result, because it makes perfect sense, right? So like you could think of this as being 2, 2, right? And it's saying that if you just kind of go like that, then there's that 1 over root 2, 1 over root 2, and over here is the, minus 1 over root 2, minus 1 over root 2. So it has given us, the method has given us the points furthest and closest to the line from the circle, right? But, I mean, this is a beautiful, I love this example, it's just beautiful. And it just makes so much geometric intuition, right? The places where these two curves are closest is where their gradients match up, right? It's where the gradient to the line and the gradient to the circle are collinear, which is just there. But this example is pretty cool, but this example is why I like Edwards. I mean, this single example to me, I think it increased my respect for Edwards considerably. This example is just nuts. So take a surface and another, this is an n minus m manifold. This is a n minus k manifold. All right, so we've got m constraints and k constraints both in our n. So something like m, something like n. We're trying to find the 2 points which are closest on these. All right, so make x a point in here, make y a point in here. So it makes it a 2n dimensional problem. And so you're trying to make I messed it up, that's supposed to be x minus y to stick with Edwards. So we want to make that as small as possible. Our constraints are that g of x is 0 and h of y is 0. That means that x is on m and that y is on n. Beautiful. Lagrange multipliers, here there are m plus k of them. There you go. You calculate them. And this is a straightforward calculation. It's nothing. It's quite understandable once you get used to this stuff. So you calculate the gradient of f, it just works out to x minus y minus x. Short calculation, very natural. And these are those. And so, again, this being equals means that this x minus y is equal to the sum of the gradients of the x of the g's, and y minus x is equal to the sum of the gradients of the h's. So we've got x minus y is equal to the sum of the gradients of the g, but it's also equal to minus the sum of the gradients of the h's with the appropriate Lagrange multipliers. But what does this say? It's so beautiful. I mean, it just says that the place where you're closest is the place where you can match up the normals to the two surface. So it's just, but the beautiful thing is I can't even visualize what this is, but it's just a natural generalization of example 9. It says that the closest 2 points are the points where, these guys match with those guys, so to speak, with a minus, of course. These are like the gradients to the g's. These are like the gradients to the h's. But it doesn't have to be a single one. You can take somehow you get a linear combination of these gradients and those gradients in such a way that they match up. And when you can do that, well, that's that's when you're closest together or furthest apart on these two surfaces. Now, of course, if the surfaces are both compact, then you can be assured that the solution exists, in fact, both closest and furthest. But if either m or n wasn't compact, then there's really no guarantee. And yet, sometimes there is. See, because even though the line was not compact, the circle being compact made it somehow work. But anyway, so that's Lagrange multipliers in a nutshell. I've given you guys a homework problem, Lagrange multipliers, which is just wonderful. That has to do with our next topic, which is quadratic forms and the problem of multivariate Taylor expansion. So I'll get to that next, and hopefully I'll be brief. Thanks.